Good morning. Today we're starting a new series of lectures about structural analysis. So this is about looking at how a system is built by interconnecting individual subsystems and components, and how all of them concur to provide a system functionality, and how, when one of these components is faulty, how this can lead to failure of the entire system. First of all, we start with introducing some useful concepts that are graphs and finite state machines. So let us start with the first topic, an introduction to graphs. You probably have already seen a lot of graphs because they are actually used in a lot of places. So you can have seen social graphs when you described friendships or other interaction between people by a graph where you have nodes that represent people and edges that represent interconnection between them. So these are friends, these are friends, these are friends, and they are connected together by what is called an edge. But you may also have seen other kind of graphs that represent, for instance, the structure of technical systems. This is an example of a graph representing how airline connects airports. So you have nodes representing airports, and you have edges when there is a flight between two airports. And this example here is really dense, and you see big clusters in the United States, in Europe, and in this part of Asia here. So graphs are powerful because you can see they are a visual way to convey how a system is structured. So in the case of airports, it would be interesting to look if there are key airports that, when not functioning, can bring down a lot of connectivity. And this actually is what happens because airports are not all the same. There are very big important ones that are called hubs, like the airport in Amsterdam in Europe or the airport of Chicago in the United States. And they are connected to pretty much all other airports, all other major airports. So if one of these hubs are down, then connectivity can be lost. So there is no longer a way to fly from one place to another. And you can see it, for instance, maybe this here can be one of those clusters. So it is represented with a bigger node, and they have a lot of edges coming in. But let us now go back and provide a more formal introduction to what is a graph. A graph is a pair of two objects. The first is a set called the node set, while the second one is a set called the edges set, and we denote with an E. We can have as an example this simple graph here with 1, 2, 3, and 4 edges, and they are called N1, N2, and so on. And they are connected, for instance, like this. N2 and N1, N2 and N4, and then N2 and then 3. In this case, then the N set contains these elements. So N1, N2, N3, and finally N4, while the edges set contains the following. One first edge between N1 and N2, which is called E1, 2. Then an edge between N2 and N3, and finally an edge between 2 and 4. So while this was the intuitive graphical way of representing that, this is the formal way, defining these two sets. We can also introduce another way to define the set is through what is called the adjacency matrix. Adjacency matrix. It is a matrix that we denote with an A. It has as many rows and columns as the number of nodes. So in this case, 4 rows and 4 columns. There is a 1 in the position ij if there is an edge between node I and j. So in this case, we know that we need a 1 in position 1, 2. So we are not considering self edges. So we don't consider the edge between node 1 and itself. But we know there is 1 between node 1 and 2. No node with 1 and 3. No node with 1 and 4. Then, second row, we look at node number 2. It has a connection to node number 1, no connection to itself, a connection to node number 3, and a connection to node number 4. Then, for node number 3, similarly, we have no connection to 1. Then we have a connection to 2, no connection to itself, and no connection to 4. Finally, for node number 4, we have only one connection to node number 3. So we have a 1 here, and all the rest is 0. One thing that you may notice is that this matrix is symmetric across the main diagonal. You see? And this is because the nodes here have no preferred orientation. So we have just drawn a line. So if there is a node between an edge between node 1 and 2, there is also a connection between node 2 and 1. This is one general case, but we can also consider when there is an orientation. And in this case, we are using an arrow to indicate, for instance, there is a connection from 1 to 2, but there is not from 2 to 1. And for instance, then we have a connection from 2 to 3, and we have a connection from 4 to 2. So if you look at this connectivity as the possibility of moving from one place to another, so every node is a place, let's say a city, it is like saying that there is a train, for instance, taking you from 1 to 2, but there is no train taking you back, which is strange, but this is just an example. And then there is a train taking you from 2 to 3, and then the train taking you from 4 to 2. So if you think that as indeed connectivity, you see that there are some nodes from which you can reach other nodes, but not always nodes are reachable in this example. So for instance, if I start in node 1, I can go to 2, I can go to 3, but I cannot go to 4 because the connectivity is the other way around. If I start in 4, I can go to 2 and 3, but I cannot go to 1. Graphs can be described furthermore according to their own structure. And so we have some examples here of possibility with the same set of nodes of defining edges in different ways such that you get different kind of graphs. One possibility is that edges are random. So for instance, you have these connection, and we assume they were made at random. So it could be like you go into a place and you start making friends in a random way. Another structure could be the one that is called the regular. The regular graph is, for instance, this one. And this regularity condition is based on the number of edges that you have for each node. you see here that every node has exactly 2 edges. And in this particular example, we also have that every node is connected to every other node through some possible path across edges. Another possibility is the complete graph. And as you can imagine, the complete graph is the one that has all the possible edges. So every node is connected to every other. So we connect the first node to this, and these. Then we connect the second to the first, these, and these, and so on. So it's getting a bit messy. We need to add this one, and finally this one, and this one as well. Oh no, we already had that. And then we have a kind of opposite example, that is the disconnected graph. It is a graph where you have only few parts and few connections, and you see that the nodes get divided into 2 islands. So these nodes can reach each other, these nodes can reach each other, but there is no way to go from this island, actually this is subgraph, to this other. Then we have another interesting and important structure, that is the tree. The tree is something like this. And if you draw it, you see immediately why it is called a tree, because like real trees, there is a trunk and there are individual branches. And the properties of this graph is that there is no redundant edge. There is only one way to go from one node to another. So you can go from every node to every other node, but there is only one way. So there is no redundant path. So for instance, from this node, I can take this path to go here. Or from this node, I take this path to go here. But there is no extra like this one. And then another example of structure that we're going to use later is the bipartite graph. So the bipartite graph is a graph where the nodes are divided into 2 sets. Let's say these and these. And you have edges going across from one set to another, like these. But you don't have edges that are from one node in the same set to another. So nodes from this set A have an edge to some nodes in this set B, but no edge inside A, no edge inside B. And we will see later how this kind of structure is useful to describe dynamical systems, and in particular the relationship between equations and state variables. Edges can seem quite simple tools, as you have seen until now, because actually we just described them in terms of nodes and edges, and this allows you to study properties, as we said, as connectivity, but not so much else. But graphs are very powerful because we can extend them with extra properties such that we can solve problems or run algorithms using graphs. And the first thing that you can do to a graph is to add something that is called a weight. And let us draw an example. So again, we consider a number of nodes, one that we call A, like Amsterdam, and then one that we call D, like Den Haag, and one that we call R, like Rotterdam, and one that we call U, like Utrecht. And then we draw edges, and shouldn't come as a surprise. Now I'm making up, I'm not sure about which roads are present or not in reality, But these edges describe roads that connect these cities. And now we add the new things, weights. To each edge, in this case, we attach a number. Let's say this number is 40. This number is 15. This number is 60. This is 50. And this is 40. Again, I'm making up because I don't know exactly the distances between cities. But let us assume these numbers, these weights that I attach to the edges, represent distances. And then on this graph, you can solve one problem that is quite familiar. That is the problem of finding the shortest path between two cities. So if I want to go to Amsterdam, starting from Rotterdam, what is going to be the shortest route? So in this example that is not realistic, actually it turns out that if I take the direct road, I need 60 kilometers. But if I take this other road through Den Haag, the total is 55. So actually the shortest will be going through this path here. Going from Rotterdam to Utrecht and Amsterdam will take longer because the total here is 90. So we can initially say, okay, the shortest path is this one. So this is what tools like Google Maps are doing in order to find the best route for you. And the algorithm that is used is called the Dijkstra algorithm. In reality, Google Maps is not doing this, but is attaching a different weight to every edge. Not the length of this stretch of road, but how much time does it take to go through that road. So for instance, a path can be shorter, but if you have more traffic there, it is taking more time. And this means that these weights can also be dynamic and change over time. So the length of the road is not changing over time, but traffic is. So the time you need to go through that is also a dynamic quantity. Then, if we talk about dynamics, graphs indeed can serve also other interesting purposes in this field. So you can use graphs to describe the behavior of dynamical objects. An example that you know very well about, for instance, are flowcharts. So a flowchart is a graph where nodes are states and operations that you are doing or some computer software is doing if you describe computer software. And edges represent the fact that you move from one state to another, so from one activity to another, according to some conditions. So there are edges that have no conditions attached, so you start reversing them as soon as you complete the previous operation. And then you have edges that have a condition on them, like edges that answer to a question with either a yes or a no. So this is a funny example from a TV series, and it is about an algorithm for making friendships with somebody. And so the first thing is that you start from this node. So even if it is not notated with a round circle, it is still a node. And you start placing a phone call to somebody you want to make friendships with. And you, as soon as you start making this, you traverse this edge and you get to the next node. And the next node is asking a question. Is the person home or not? So they are still assuming that you are called a landline number. So you have two edges that are getting out of this node, and one you traverse if the person is not home. So you are leaving a message in their voicemail. Or yes, if the person is home. And then you continue in this case, and you start asking questions about the person, what they like to do, if they want to have a meal with you, and so on. So that's funny. You can have a look at this algorithm. There is also another class of graphs that can represent the behavior of dynamical objects. And this is the state transition graph. A state transition graph is a more formal definition of a behavior than the flowchart. So you may have seen these in some courses about computer science, but if you don't have that background, you can just have a short look at that. And we start with an example that is the easiest way to understand. So this is a state transition graph about a door. So one door can either be open or closed. And these two states are encoded using two nodes. So you have one state that is telling you the door is being opened, has been opened. And one state that tells you the door has been closed. And so the door has no other behavior. So you can just move between these two. So if you are in the state the door is opened, you can close the door, traverse this edge, and then you get to the door is closed state. If the door is closed, you have only one possibility, it's to traverse this edge, which will open the door and take you back to the initial state. You see that there is some more notation actually. So inside each node, each state, there is also one activity. That is the activity that you perform when you enter this state. So if the door is closed and you want to open that, somebody tells you, open the door, please. You traverse this edge, and the first thing that you do is you open the door. And then you are finally inside the state the door is opened. On the other way around, in this state, what you are doing when you get there is to close the door. So in this case, the formalism is also extended with respect to the basic definition of a graph. So we have that our node set represents now the states, and the edges represent transitions. So in the plain definition of a graph, we had edges that were represented with either two numbers, a 0 or a 1. So at 0 if no edge was present between two nodes, and a 1 when an edge is present between those two nodes. In the case of a state transition graph, this is no longer to be some static quantity, but it will become something dynamic. So we can define the transitions then as functions that has some input in a given domain that we can call u, and whose output will stay into this set with two possibilities, 0 and 1. So what is meaning this? So the transition, that is the edge, has no static predefined value, but it is a function of an input, and this function will have two possible values, 0 or 1. So for instance, in the case of this example, we have the node 1 and 2. 1 is the door is open. So the transition from 1 to 2 is going to be a function defined in this way. We denote it with tau 1, 2 is a function of some input u, which is equal to 1 if u is equal to close, and 0 if u is equal to open. So here we are encoding the fact that somebody is telling you to open or close the door by saying my finite state machine or finite automaton has an input, and this input can either be open or close. And in this example, a transition from state 1 to 2 is going to occur, 1, when the command is close. but it is not going to occur if the command is open. That is, if the command is open and if I am here, I will stay here. These kind of graphs are going to be useful for us when we are going to describe how different components can provide different services in different conditions. So these states then will describe the condition a component is in and how I can switch a component from one condition to another. So for instance, I can have a system providing measurements to a control system. And you have the normal behavior when all the sensors are working. And then you get, for instance, that the measurement is provided with high accuracy. But then, if one of the sensors is breaking down, you move to another condition where the measurement is provided, for instance, with less accuracy. Now we are going to look into the other kind of graphs that we talked about before, and it is useful for structural analysis. And it is the bipartite graph. So as we anticipated in a bipartite graph, the node set is partitioned into two. So we can define this formally by saying that the graph G is equal to a node set that has two components. And in this case, we are going to call the first one C, and the second one we called Z. And then we have the edge set. It is why we did that in our case. It is because we want C to represent constraints in our system, and we want Z to represent variables. With constraints, I mean equations that are defining variables in your system in terms of other variables. Let us draw an example to make things easier. So let us introduce some nodes that represent the variable subset, the second one, and then some other that we draw with small rectangles that represent constraints. So they don't need to be in the same number, and usually they are not. Let us assume that we have this kind of connectivity. The nodes on the top, we said, are variables. We call them Z1, Z2, and Z3 and 4. And these are the constraints. We call them C1 and so on. So that's the Z, and the set C. So what is going to represent this graph now? This graph is representing the fact that one variable Z1 is occurring in one equation C1, where the variable Z2 is also occurring. And similarly, Z2 and 3, both they occur in C2, and Z3, 4, and 2 are occurring in equation C3. For example, the equations can be as simple as this one. We can have the equation C1 telling us that Z1 is equal to 2 times Z2. Then we can assume that C2 is such that Z2 is equal to 3 times Z3. And then C3 is telling us that Z2 plus Z3 plus Z4 is equal to 0. So if you have this system of equations, and if you are not interested in solving it numerically, but you just want to look at its structure. So the structure of this system of equations is represented by this graph. And just by looking at the structure, you can get useful information whether this set of equations can be solved or not. So one thing that you can immediately notice is that we have 4 variables. So in the case of the equations, 4 unknowns and 3 constraints. So we already know that this is underdetermined. So you cannot solve it exactly. So there are infinite number of solutions. Even if we add one constraint, just the number of constraints is not important. So let us assume we add one more, and we don't connect it to any node here. It's like saying this constraint is about something else. Or the fact that it's not connected immediately shows you that this is not adding any information, so you cannot actually solve the systems of equation uniquely just by adding this. If you had a situation like that, then at least from a structural point of view, you can solve in a unique way this set of equations. So now, this set of equations is just an example. They are algebraic equations, but you can use the same approach also to describe a set of dynamical equations. So the one that we use to describe the behavior of a dynamical system. One more thing that we want to do before moving forward is to further anyway split these sets into 2. It is useful to split the set of variables into a set of known variables and one of unknown variables. And similarly, you can split the constraint set into 2. One that is called CK, the set of constraints on known variables, and one on unknown variables. So this set here is the set of constraints that link only known variables with other known variables. And this is the set of constraints linking unknown variables with either unknown or known variables. And why this subdivision is useful? It is useful because you can assume that into this set of equations, some of the variables are initially known, and the others are the one that you need to solve for. And then this is going to change the fact that you can find or not a solution. So in the case of dynamical systems, the role of known variables will be taken by measurements. So if in a dynamical system you have a measurement, you can assume that you know that variable, up of course to uncertainty. And then you can look at this graph and see if you can reach unknown variables, which means if I'm starting from a one variable that I know and I can solve all the equations that I have on my path, I can find the value for the missing one. For instance, in this example, let us assume that we know variable z1 and we know variable z2. Then the question is, can we solve for z3 and z4? And without even looking at the equations, we just look at the structure, and we see that the variable z3 is occurring in this equation, C2. And the only other variable that is occurring in this equation is z2. But we know that, which means that we can invert this equation to get the value of z3. So for instance, we say that this equation is simply z2 is equal to 3 times z3. Well, then z3 is simply obtained by taking z2 over 3. And then we can look if we can find the value of z4. And indeed we can, because z4 is occurring into this equation, C3, where z3 and z2 are occurring. But z2 is known, z3, we just computed it, So Z4 can be simply obtained by inverting this equation here. So the usefulness of this approach is when later we are looking at dynamical systems, where we know only a few of the variables, we can check whether using equations that we know, we can find the values of other ones. We will see now a couple of examples to clarify this. The first example is about the simple tank system that we introduced before. So we have an actuator, the plant, and the sensor. So the actuator is a pump, and given an input U, is providing an inflow Qi. Let us write the equations of this example. And we start with the tank. Our first constraint, that we call C1, tells us that the rate of change, the derivative of the tank level, is equal to the inflow minus the outflow through the drain. So we simplify and we assume that the cross-section of the tank is 1. The second equation, C2, tells us that the inflow provided by the pump is proportional through a constant alpha to the input U. Then the third constraint is telling us that the outflow Q out is equal to some constant K that multiplies the square root of the level. So the proportionality to the square root of the level comes from conservation of energy. Then we have another equation describing the sensor. It says that the measurement is equal to the level. So we don't introduce any uncertainty here. And finally, we need a last equation that is relating the derivative of h, the level, to h. And we actually need to write that out. It says that the level h is equal to the integral of the derivative along time plus some initial level h0. Once that we have these equations, we can draw a structural graph representing them. So starting from the pump, we have the input U and the constant alpha. They both go into equation C2. And equation C2 is also connected to the inflow Qi. Then I have that the inflow Qi through equation C1 is linked to the derivative of h. So let us introduce equation C1. This is linked to h derivative. But we know that equation C1 is also linked to the outflow Q0. Then what we have is that the derivative of h is linked to, as we know, to h itself. So this is C5, the integration. We also need to introduce the initial level h0, and this is linked to h. And then h through equation C3 is linked to the outflow Qo and the constant K. And finally, we have the last equation, the output one, that is producing the measurement y. Okay, we hinted previously at the fact that we can use structural graphs like this one to answer the question whether a given variable can be computed from known variables. And this is quite an interesting question when it comes to fault diagnosis. And I will show you, using this example, why. The first thing that we need to do is to introduce an orientation of the edges. So the edges that we have now, they are not oriented. We can follow this rather intuitive orientation, which is we orient these edges like this. So the meaning of this orientation is, assuming that we know the value of u and alpha, we use them as inputs to equation C2 in order to produce as output Qi. In this case, it's quite reasonable because we are assumed to know what is the input we are sending to the pump, and we probably know the value of alpha. So if we have a knowledge about the dynamics of this system, we probably know alpha. So if we are building a fault diagnosis system, this system is some software that can communicate with the control system. So we know what the value of u is. And thanks to knowledge about the pump, we can use u and alpha and equation C2 to compute the inflow Qi. And we need to compute Qi because we have no sensor in this example measuring Qi. We have only one sensor measuring the level. But let's proceed forward then. So assuming that we computed Qi, then we may use this equation, C1, to compute the derivative of h. So let's add an orientation like this. Now the issue is that we also need to know Qo, the outflow, and we have no sensor for that. But don't worry, we are getting there. So let's some way assume that we got here and we computed h dot. And let's see if this assumption is consistent. If we were able to compute h dot, we can use this equation to compute h. We are just missing one thing. We are missing h0, the initial value of the level. But this is not really an issue because we have a sensor. So we can assume that when we start up our system, the first thing that we do is to measure the initial value of h. So it would make sense that following this path, we can compute h. If we can compute h, we can go forward here, and using this equation, and assuming that we know the constant k, we can compute Qo, the outflow. And now finally, we go back to here, and so we see that our initial assumption was consistent. Indeed, there is a way to compute all the variables that I need to solve. You see here, there is a loop. I can solve it. Finally, if I know h, it means that through this equation, I know y, the measurement, because this equation is trivial. So why it is important that we show that we can traverse this graph, and starting from variables that we know, we can compute y. So let's highlight that. So assuming that we know this, u, we know alpha, that is, we know a model of the system. We know the initial value h0. We know k, another parameter. Then, using this knowledge plus the equations, for sure we can compute y. And this is, from the point of view of fault diagnosis, a wonderful result. And this is the entire reason why we are talking about bipartite graphs, because they are a tool to show that we have one of the things we mentioned in one of the previous lectures. We have an analytical redundancy relation here. Let's write again this analytical redundancy relation. So where is the redundancy actually? Well, the redundancy lies in the fact that y is both a variable for which we have a measurement and a variable that we can compute from other variables that we know. So we can implement the thing that in one of the previous lectures we called a virtual sensor. So we have a way to compute what the value of y should be. Should be if the equations that we have here are indeed representing our system. So now, what we could do in order to build a diagnosis system for the tank is to have some software that continuously is solving these equations and computing an estimate for y. You can imagine that this kind of software is an observer. This is what we're going to use later. And every time that we have a measurement from here, we can compare the value of the measurement with the value of the estimate. So let us call the estimate y hat. We can compare y hat with y. So it's easy to see that if the model is good, the measurements of the other variables are good, the difference between the estimate y hat and the measurement y should be small. Whenever this is no longer true, then we are going to have a symptom that we can use for fault diagnosis. And so this is what we are going to do later in the course when we are introducing model-based diagnosis using observers. But the important thing is that first we need to check whether there is a way to get this analytical redundancy relation, and then if there is a way to do, then it makes sense to build an observer, and then we can do model-based diagnosis. If there is no way to build an analytical redundancy relation, so which means if there is no way to solve these to get an estimate of y, then we cannot do that. So for simple examples, you will see that it is not difficult to see you have one. But when you have a system composed of a lot of components, then it will really make sense to use first structural analysis. And we will have another example about that. The more complex example is about a heating, ventilation, and air conditioning system in a building. So in a modern building, in every independent unit, you have a system like this one that is providing temperature and air quality control. So this system is comprised of a boiler that is providing hot water. And this hot water is split in order to heat a radiator or heat a heating coil inside an air handling unit. And this air handling unit is mixing fresh, cold air from outside with inside air that is heated here in order to provide warm, fresh air to your dwelling. So you have two functions here, heating and providing fresh air. If you want to build a diagnosis system for the HVAC example, we can start looking at the models of the components we introduced before. And for instance, we can look at the boiler. I don't want to go too much into details, but the dynamical equation of the boiler is here. What we have is a dynamical equation for the supply water. So this differential equation tells you that the derivative of the supply water is depending on this. And what you have here, you have one important term that is the power provided by the boiler. So more power, more increase in the supply water temperature. But you also have some thermal losses here. So you have the difference between the temperature of the return water and the supply water. So you have cold return water coming in the boiler. And of course, this is going to make the supply water temperature lower. And then you have also another thermal loss that is due to the fact that the boiler itself is placed inside a room that is colder than the supply water itself. So some of the heat of the supply water is lost to the environment where the boiler is present. But you can also describe this equation plus the measurement equation that we have here as a graph, and that's easier to interpret. So you see that we have variables that we consider inputs because we know them, and they are denoted with blue circles, and they are the boiler power, the return water temperature, the boiler room temperature, and the supply water flow. They enter into this equation here that represent this. And the output of these equations, so the quantity that we can compute, is the time derivative of the supply water. Then this time derivative is entering this other equation that, as before, is simply the time integration. So this is providing the actual value of the supply water, provided that we know the initial value of the supply water. And we assume that here it is uncertain. We don't have a measurement of that. And finally, this last equation here is the measurement. So it describes the fact that somewhere we have a sensor for the supply water, and is providing a measurement of that. But to make things more interesting and realistic, we assume that the sensor has some noise. So there is some uncertainty that we represent with orange variables. So we have the blue that we know, the green that we measure, the orange that are uncertain, and the white that are what we want to compute because they are not measured. So this structural graph is still simple because you see that up to the uncertainties, you can compute the supply water from what you know. But things are less simple when you consider all the components together. So we have the boiler, we have the splitter, radiator, the air handling unit, the building itself, which is a cause of heat loss. So if we put everything together, we can write equations for every single component, and every single component will have its bipartite graph describing the structure of its equations. So for instance, here you have the equation for the building envelope is called. So this is describing how we lose heat to the environment. And then once we have all these individual structural graphs for the components, we can connect them because we know that some variables in one component are influencing the behavior of the others. For instance, in the boiler, the temperature of the supply water is influencing a lot of other things, like the radiator that is here, the air handling unit that is here. So if you consider the complete HVAC example, so the structural graph is all this. Now you see that answering the question whether some quantity is computable or not, if I can get analytical redundancy relation, is not so straightforward. So we will not go into the detail of how to answer this question, but it all boils down to try to traverse this graph and find a path from variables that you know to variables that you don't know. So if you can find this path, then you are good. It means there is an analytical redundancy relation involving the variable where your path is ending. So in this lecture, we provide a some overview of graphs, and in particular, two kinds of graphs. One are the state transition graphs that describe a finite automaton or a finite state machine. And then we describe the bipartite graphs and how they can be used to describe the structure of a system. So these were preliminary blocks that we covered in order to prepare for the next lecture, where we are using these to introduce a tool for structural analysis that is called the components and services model, that will formalize what I already introduced to you, the fact that you have systems comprised of subsystems and components, and they are connected together. Thank you.